Hello, everyone. My name is Seth Miller. I am the team leader for this project. I am here with Thomas Fiesca, Zach Bosley, and Jake Stevens. We are Project 21081, the Solvent Waste Recovery Team. I'm going to pass the mic over to Jake so that he can talk about the project goal and overview.
Diving into a quick overview of the project, we have a polymer facility that must install a waste recovery system for impending re-permitting, increased environmental image, and most importantly, the astronomical amount of company savings. The re-permitting environmental image will be increased or achievable by the installation of the waste recovery system, reducing the amount of waste expelled to the environment. There are three primary waste streams in this facility currently. Two of them are water streams with two separate impurities being acetaldehyde and ethylene glycol. There's also a vented air stream containing methanol and acetaldehyde. The current facility expels all of the waste to the biopond, and the goal of the project is to recover/reduce the chemical waste from the established polymer facility, and we must recover 90% of the stream contaminants, and if the solvent is chosen to be reused, it must be of 99.5% purity or greater, with water acting as the major impurity. Diving into the acetaldehyde waste stream, it is a water-rich stream where acetaldehyde is the product for recovery. The water richness or the large amount of water in the stream causes separation issues. There is also 10% flow rate variations and 2 to 5% concentration variations. Flash distillation was chosen to reduce the amount of water before heading into a multi-stage binary distillation column that achieves ultra-high purity and recovery of the desired solvent. There's also a pre-column condenser that aids in column operating and improves column hydraulics. Here is a quick process flow diagram of the design process for this waste stream, where the feed from the polymer facility on the left goes into the column condenser and then is fed into the first flash drum, where the overhead vapor product is rich in acetaldehyde, and then is fed into a second flash distillation unit where the overhead is once captured and compressed to re-equilibrate to atmospheric conditions for the column operation, where the top rate, there is a 99.5% pure acetaldehyde that is getting fed back to the polymer facility.
Thanks, Jake. Now Zach will talk about the ethylene glycol waste stream.
So the ethylene glycol separation has several similarities to the acetaldehyde separation. The feed is a water-rich liquid stream containing ethylene glycol in varying concentrations between 2 and 4% by volume. A series of flash drums is used to remove the bulk of the water, utilizing increasing temperatures and pressure drops between each step. The final flash drum feeds into a distillation column to achieve the 99.5 mole percent product purity and the 90% recovery. A distillation column with the dimensions shown here will satisfy these requirements under all of our conditions. And this is our PFD for the separation. The 5 flash drums are modeled as steam heated jacketed vessels. Each one will feed its liquid stream into the next. Between each drum is a pump to pressurize the stream before it undergoes the next flash operation. The vapor products from the flash drums, as well as the partial condenser of the column, are emitted to the atmosphere with only trace amounts of ethylene glycol. And our desired product is in stream 32 near the bottom right of our diagram.
Thanks, Zach. Now Thomas will talk about the air waste stream.
Air scrubber for this process is being used to strip out acetaldehyde and methanol contaminants from the waste airstream. The scrubber for this design is a 5-stage carbon steel rastered ring packed tower with a height of 5.08 meters and a diameter of 1.2 meters. The unit is equipped with 2 vane axial fans to supply the flow of contaminated air. The physical size of the tower was determined by taking into consideration the flow rate of air, which can reach volumes up to 80,000 cubic feet per minute, as well as the water stream flow rate, which after expansion plans was set to deliver around 18,000 kilograms of water per minute. The packing material and number of stages was determined by considering the mass transfer coefficients of both acetaldehyde and methanol by means of two-film theory, as well as their solubility in water. The overall sizing of the unit was also confirmed by Aspen simulations. The purity of air that will be sent to the atmosphere was determined to be 96.25% under normal operating conditions and 99.76% purity for the EPSA conditions. This allows for the air to remain under the short-term exposure limits of both acetaldehyde and methanol set by OSHA and the CDC. All spent water containing the absorbed contaminants will then be sent downstream to the biopond for degradation. Here's our air scrubber presented as the main block in the diagram, in which there are 2 inlet streams, one being clean water, the other being contaminated air, and the 2 outlet streams. The stream at the top of the column represents the resultant purified air and water vapor being expelled to the atmosphere, and the second outlet stream being contaminated spent water that will be sent to the biopond. As seen in the diagram, both the inlet and outlet water streams are both equipped with emergency bypass valves with appropriate process control to open and close valves in case of system shutdown or if the process becomes overwhelmed with upset conditions. The control system monitors the water flow of the inlet and outlet water streams in order to open and close the emergency valves to temporarily divert water to the biopond to reestablish necessary set points. The control system will also monitor the liquid level in the tower to prevent flooding, which would eventually lead to a decrease in air purity.
Thanks, Thomas. I will now go over the biopond and finish up with project economics. The biopond acts as the final facet of the process where all the process streams end. Each previous process has at least one stream that ends in the biopond, which is either a liquid product stream or a bypass stream. The biopond utilizes a mixture of algae and bacteria to convert the acetaldehyde and methanol into carbon dioxide and water, and will be designed as a facultative pond. This specific type of pond is a combination of an aerobic surface and an anaerobic floor region that will ultimately reduce the smell being emitted from the pond, thus satisfying any nearby residents complaining about the smell. Another benefit of this type of pond is the relatively small amount of maintenance required to operate the pond, requiring only a desludging once every 5 to 15 years, making the pond one of the more efficient wastewater treatment methods. Since our project focuses mainly on the solvent recovery, not much was known about the kinetics regarding the actual degradation of the waste products, but the biopond was present before this project began, which means that all that was required was an expansion of the existing pond. It was found that the pond went from roughly 1,600 cubic meters to 3,300 cubic meters, with expenses being covered in the following slides. This expansion was designed around the 36-hour retention time that was determined before the project began and took into account the max flow rate that would ever come into the pond at once, which coincided with all the process streams going through the bypass valves and straight into the pond. This slide contains the process flow diagram for the biopond, while also including the file pieces of equipment for the waste airstream and the acetaldehyde process stream. The pump shown under the biopond is indicative of the one aeration pump necessary to circulate oxygen throughout the aerobic portion of the pond, while also indicating the presence of a backup pump that is utilized when the pump undergoes repair or cleaning. Lastly, I want to talk about some of the project economics. The total bare module cost, as shown in the table, refers to the summation of the bare module cost for all items of processed equipment, including fabricated equipment, process machinery, spares, tanks, and computers software. The direct permanent investment is the estimation of the purchase cost of required equipment and the cost of installation. If you add the cost of contingency, the cost of land, any applicable royalties, and the cost of starting up the plant if necessary, this gives you the total permanent investment. The total depreciable capital is the investment for the desired production rate and year. And the total capital investment is a one-time expense of the design, construction, and startup of a new plant or the revamp of an existing plant, as is the case in this situation. The total annual cost of manufacturing is the sum of direct manufacturing costs, operating overhead, and fixed costs. The general expense is referred to activities that are conducted by the central operations of a company and are financed from profits made by the company from their operating plants. If you combine these two values, you will end up getting the total annual production costs. And on the last table shows the annual sales or savings that this project will incur for the polymer facility plant if we were to sell the acetaldehyde that was removed from the waste streams. And that is all for our project. If you have any questions, there will be a separate Q&A link that will be provided. Thank you.